Another hypothesis of interest is whether a given predictor variable, say xi, is statistically useful in predicting the variance of the response or independent variable y or not. Remember, the coefficient of the ith predictor variable xi is beta I. And if beta I is equal to 0, then it means that whenever xi changes by 1 unit, the response variable, that is the dependent variable, changes by 0 units, which means there is no change. And therefore, that predictor variable is not useful at all in predicting the response variable. Now, the hypothesis that we test is therefore as follows. This one is the null hypothesis that the predictor variable xi is not useful. That is, the dependent variable xi is not useful, which means its coefficient is equal to 0. So that when it changes, when xi changes by 1 unit, there is 0 change in y. Therefore, we can as well do away with xi. The alternative is that the coefficient is not equal to 0, which means predictor xi is useful. The test statistic we use is the t, just like in the case of the simple linear regression. And t is obtained by dividing the estimate of the coefficient beta I with its standard error, and this one, and then comparing it with the critical value, that is t at 1 minus alpha over 2, and then n minus k minus 1 degrees of freedom. Notice we are using the degrees of freedom of the error term, n minus k minus 1 degrees of freedom. And now the decision rule is as usual. If you get the computed value in absolute, that is ignoring the negative sign, if that value is greater than the table value, then you reject the null hypothesis. You reject this hypothesis, and you conclude that the predictor is useful in predicting the variance of your dependent variable or your response variable. Remember, the two refer to the same thing. Now, to be able to test this hypothesis, we require the output from the computer software, and the output is found in a table that is called the coefficient output table. And this is the way the coefficient output table looks like. It has got the variables in the model. Like in this case, there are only 4. This is not an example. This is just an illustration. And we'll see the example we did earlier, just here below. And then here, this column shows you the estimates of your coefficient. You remember you saw this a little bit earlier. And then here, you have got the standard errors. And then you've got the t-values here. If you divide the estimates, these ones, by their standard errors, you get the t-values. So if you divide this by this, you get the t-value. Divide this by this, you get the t-value. And now we can use these t-values to make a decision whether to reject or not to reject our null hypothesis. The other alternative is to use the p-value, and the computer output also provides us with the p-values. And here are the p-values now. This is the computed probability of computing type 1 error, and we can compare these values with the level of significance. You will find that given a computer output, it is easier to use the p-values than the t-values, because the t-values require you to go back to compare this with a t-table value. So you got to read off the value, but here you don't need to read off any value from the tables. So the decision rule using the p-value is to compare the p-values and reject the null hypothesis whenever your p-value is less than the level of significance. Let's look at an example. So from the previous example, let's evaluate at 5% level if the coefficients of the radio and the newspaper advertising expenditure are significant in predicting sales, and also examine whether at 5% level the constant is significant. To be able to answer this question, we need the computer output of the result that we obtained when we ran the data. And here is the part of that output. You had seen this one earlier. So you have got the estimates of the coefficients and the constant here, and these are their standard errors. So if we want to compute the t-values, we go to divide this and divide the estimate by the t-value, and again we divide this one by this, and then we get the computed values, and those are the computed t-values. So the result you get is this one, you get this, when you divide this one you get this, and this one you get this. And now those are our computed t-values. Now we have to get the critical value to be able to compare with the computed t-values. Now remember, our alpha is equal to 0.05, and so if we take 1 minus alpha over 2, we get 0.975. So the critical value that we are looking for is the t at 0.975, and 22 minus 2 minus 1 degrees of freedom, which is 19, and this value you can read off from the tables as we showed you earlier. It's going to be 2.9093. Then we can now compare. For each of these values, we compare with this value here. So if we compare, we will see that in this case, the radio, this one is greater than 2.09. This is greater than 2.09, but this one is less. So that means the radio is significant in predicting sales, and newspaper expenditure is significant in predicting sales, but the constant is not significant because it is less than this value here. So that's what we're saying here. You compare and you conclude that each is significant or not significant, which we have already gone through that. So from there, you can see that the radio and the newspaper adverts are significant. The constant is not significant because 1.23 is less than 2.09. Alternatively, we can use the p-value to arrive at the same result. And if we use the p-value, first of all, we can get the results of the p-values. And here are the results of the p-values. And you can see that this p-value is less than 0.05. It is less than this value here, our level of significance, which is 0.05. And this one is less than, again, 0.05. But this one is greater than 0.05. And so we conclude that constant is not significant because its p-value is greater than the computed p-value, which is its p-value is greater than the level of significance alpha. Another way we can test the hypothesis above is using the confidence intervals of the coefficients. You remember from the simple linear regression case that the 100 1 minus alpha confidence interval for coefficients beta I is going to be given by this formula. And you will have the standard deviation. This is the standard deviation, which we get from the computer output. And BI, the estimate of beta I, is also provided in the computer output. The computer output that we use to compute the confidence intervals will be presented in a table. And we have got, of course, the coefficients in the first column, the independent variables in the first column, and then the coefficients, and then you have got their standard errors. Now, if you want to compute the lower limit, you simply put the negative sign. So B1, the t-value that is obtained from the tables, plus the standard error of B1. And then the upper limit, you put the plus sign, you use the plus sign. And that's how you get the confidence intervals. If 0 lies within here, within this, it lies inside here, in between here, then that means that that particular coefficient is not statistically significant. That will happen if the lower limit has got a negative sign and the upper limit has got a positive sign. Otherwise, if both of them have got the same sign, either negative, negative, or positive and positive, then in that case, the predictor variable is statistically significant. Once again, let us use the previous example to illustrate how you can compute the confidence interval. And we want to compute the 95% confidence interval of the coefficients and the constant. So we go back to the computer output, which is provided here. This is the computer output. You can see we had two independent variables plus a constant. Your dependent variable is sales. These are the estimates that we obtained, and these are the standard errors. So now to be able to compute the confidence intervals, we use this formula, which is going to be equal to BI, that is the estimate. Okay, this one here, sorry. And you get the table value, and we had seen that the critical value at 95% confidence interval is equal to 2.093, and then you multiply that value by the standard error of the estimates, which is this one. So this is how then we compute the confidence intervals. So for the first one, you have got the estimate for radio is 13.81 plus or minus 2.09, which is this one, times 1.759. And then you will get the result here. So the lower limit is obtained by taking 13.081 subtract that 3.682, and you get this value. And then the upper limit is you use the addition, and you get 16. You can repeat the same for the others, and these are the results that you will obtain. And that's the way you get the results. Notice that for the constant here, the lower limit is negative. Can you see the negative sign here? This one here. It's negative. Maybe let me remove this bit so that you see the negative sign properly. So you can see the negative sign, and this one is positive. So that means 0 is somewhere in between these two. But for the others, this is positive, and this one is also positive. So 0 is somewhere down here, and this one is also positive and positive. So 0 is somewhere down here. So these two are statistically significant because 0 is not contained inside. But the constant, as we had seen earlier, is not statistically significant because 0 is somewhere in between the lower limit and the upper limit. Let's go over all this using one more example, and here it is. Economists studying industry organization are interested in the relationship between firm size measured in annual sales in millions of dollars and spending on research and development, R&D. One might also be interested in the effect of profit margin, that is profits as a percentage of sales, and sales on R&D spending. Using the data from 32 US firms in the chemical industry, the following partial output was obtained. I got this one from Woodridge. So this is the output, but it is partial. I've cut out some few things because I want to illustrate for you how you do the computations. So you have got the first table is the ANOVA table that shows you the source of error, model, and the residual, the sum of squares. And now you can compute your mean sum of squares. If you divide this one by 2, you'll get the mean sum of squares. You will notice from this one, which is the coefficients table, that your independent variable is research and development, R&D, and your independent variables are sales and profits here. And then, of course, we have the constant. So if you come back here, if you divide this one by 27, you get your mean sum of squares. You divide, you get your mean sum of squares. This one, usually we don't require it. We don't require this one. And then if you divide this, you get the t-values. Divide this, you get the t-values, and divide this, you get the t-values. So let's see the questions that we are supposed to respond. So here are the questions. And the first thing we asked is to interpret the meaning of the coefficients, test at 5% level, significance of the model, and so on. You can read all this on your own. Now, first of all, we want to interpret the meaning of the coefficients. And this is we use this output. This is the coefficients table, and you can see the value of the coefficients here. So this is what you use to get the model. So your estimated model is going to be obtained by multiplying the sales. First of all, you take the constant, which is minus, and then plus the sales times its coefficient, the profit times its coefficient, and that gives you the estimated research and development model, estimated model. Now, when you divide, you have to first of all, now because we want to interpret the meaning, we now look at what does this coefficient mean and what does the constant mean. And from this output, for each additional unit, which means, remember, it's measured in million shillings, additional $1 million, not shillings, of sales, which is this one here, holding profit margin at constant, the research and development expenditure increases by 0.0415 units. But that means for $0.0415 million, and that one will give you, I think, $415,000. And then you can get the coefficient for the profit, and it means that for each additional unit of profit margin, which is percentage, profit margin is expressed as percentage. So if you increase profit margin by 1%, holding sales at constant, then your research and development expenditure will increase by $0.0859 million. So that's how we interpret the coefficients. We are also asked to test at 5% level the significance of the model. In that case, we use the ANOVA table. And this is the way the ANOVA table looks like, as you can see it here. So if you divide here, divide this, divide by 27, you will get this result. And here, when you divide, you get this result. Okay? Now, if you divide these two here, divide these two, if you divide them, you get this result, the F. So in order to test this model, the hypothesis that we have is that the model is not significant versus that the model is significant. So the critical value is going to be the F at 2 degrees of freedom and 27. Normally, just look at this, the degrees of freedom of the model and degrees of freedom of the error. This is the numerator degrees. This one is the numerator degrees of freedom, and this one is the denominator degrees of freedom. Then you read off from here and you get 3.35. Now compare that with the computed F value, and our computed F value, don't forget, is this one here. This is our computed F value. So if we compare it with this one, we notice that we will reject the null hypothesis, this one, that the model is not significant if the computed value is greater than 3.35. And so since 27.996 is greater, we reject and conclude that the model is useful at 5% level. In part C, we are asked to test at 5% level the significance of the sales and profits in predicting. So we want to test whether are these coefficients statistically different from 0 and the constant. So we have this output with us here. And so the first thing that we do is we get the t-values by dividing these values, divide this one by this, you get the t-value, divide the coefficient there by 0.13007, you get the t-value, divide this by this, you get the t-value. And if so that's how we've got the t-values when we divide. And then to determine the critical value at 5% level, which we had done earlier, and we had not done it earlier, sorry. So this one we are using 0.975 because our critical value is 5%, and our sample size is 32, not 30, 32, so we will have 30, no, it's 32. It's 30. You have 30 minus 2 minus 1, and you get 27, and the t-value is 2.05. So compare that one. Any predictor variable here, or independent variable, whose t-value is greater than this value is significant. So if we compare 3.53 is greater than 2.05, but this one is less. This one is less. So this one has a problem, it is not significant, and this one also is less. If it's also less by 2.05, so with only the sales are significant. So if we compare that, we will see that the sales are significant, but the profit is not significant, and the constant is not significant because their t-values are less than the tabulated t-value. Finally, we are asked to construct the 95% confidence interval for the model coefficients. Again, we go to our computer output. This is the result we have. And of course, if you are running the computer gives you everything, including the confidence intervals, but I've left that one out because I want to show you how you compute them from your calculator. But if you run a computer output, it will give you all the information that you need. It's only for you to pick it up. So now, we first of all compute the confidence intervals. We know that the critical value at 95% we have seen is going to be equal to 2.05. So we compute the confidence interval at 95%. It will be equal to the coefficient, which is this one here, your coefficients here. And then you plus or minus. Remember the lower limit you use the minus, the upper limit you use the plus, and then take the table value minus the standard error. So this is the result that you get. For example, if you are getting the lower limit of the sales, then you've got 0.0415 minus 2.05 times the standard error, and then this is the lower limit. And the upper limit you just add, and here you just replace that one to be addition, and you get the upper limit is this. And So you can compute the others in a similar fashion, and these are the results. Now, one of the things you will notice that is the first one, the 0 is somewhere on this side to the left of this value. But here, 0 is somewhere in between here because this is negative and this is positive. So 0 is somewhere here. In the same case here, because this is negative and this is positive. So 0 is somewhere in between them. So these two are not statistically significant. The profits, variable, and the constant are not statistically significant in predicting the expenditure of R